Our final panel of the day is also concerning modeling, used in a somewhat different way in risk assessment. This is a really fascinating development by a team of researchers who are going to present, Loisel and Zenon, Cetina from Texas A&M University, and I'll let them tell you more about themselves and how their collaboration came together. I think we're going to have Twyla come over and moderate for them. And Darcy Peter, Darcy, are you here? Darcy, you're going to come join us, please, on the stage as well.
Thank you very much.
Yep.
Yes.
Yep. You know how to use it? Yeah, good.
Well, for this last talk and discussion of the day, we invite all of you guys to join us in really coming up with a good plan so that we can do knowledge co-production. We've heard this all day. How do we integrate all of the things that we know and put them to good use so that we can ensure a sustainable development of the Arctic? So here we are. I will now invite my co-moderator, Dr. Zenon Medina Cetina from Texas A&M University. And in a very small way, we are doing co-production of knowledge because he's an engineer and I'm a scientist.
There's nothing wrong about being an engineer, by the way.
Of course not. So please come and have a seat. And in a second, I will also invite Ms. Darcy Peter from the University of Alaska Fairbanks, who is also what did I say?
Oh, no, do I just stand here?
Oh, great. Who is also a native from Alaska, Beaver, Alaska. So please join us.
Very nice to meet you. Yeah, you too.
Hey, a few pictures of a rapidly changing Arctic, from permafrost thaw slumps to changes in the infrastructure caused by permafrost dynamic changes, and also loss to sea ice platform access, coastal erosion, species migrations, et cetera, et cetera. There are lots of things changing. And they might see all this different in a sense, but they are all really connected by the fact that they are related to changes in ice, changes in the environment, and changes in human activity. And we haven't even talked about 2050 to answer your question. Well, this is one idea of what the Arctic might look like in a couple of decades, or perhaps 100 years. Maybe more people, more infrastructure, maybe more cruise ships, more farms, who knows? But how do we integrate all of these aspects of an Arctic together so that we can benefit from each other's knowledge? And we here at Texas A&M, we have developed a vision over the past 12 months, more or less, that we are here to share with you today. And pretty much the overall vision is to be building strategies to inform policy for a sustainable development of the Arctic. And what this looks like? It looks like this. Now, I know you might not be able to see every detail in here. Good news, we have a poster that is in one of the halls, and we will be there with a few students to show you all of this in great detail. But now let me walk you through some of it. First of all, we have on the left-hand side what we call threats. Threats are not necessarily a bad thing, they can also be a good thing, and they are what will be affecting the Arctic system as a whole. To give you a few more specific examples, here in neon green, we have the oceanic threats. For example, wave action would be one. In teal, we have atmospheric threats, for example, surface air temperature. In those baby blue here, we have the human threats, and those could be local or regional, like resource extraction, but they could also be global, like what happens to politics. Now, the heart of this model is the middle section here that we call vulnerabilities. This is really what the Arctic system is and what can be changed by these threats. So how can the system can be damaged, changed, or modified through in the future? Each one of these nodes, I forgot to mention, represents a process. You can think of it of where would I stick my data or my knowledge or my model simulation, for example. And each one of these arrows in gray are the connections between these different nodes. Here in the vulnerability, really importantly, we have the orange nodes, which are everything related to the cryosphere. So we have the sea ice nodes, we have the land ice and glacier nodes, and we have the permafrost and ground ice nodes. And then all of the other colors in there represent other aspects of the Arctic, such as the hydrology, the vegetation, the ocean, the humans in purple, the carbon cycle in dark blue in the bottom right, etc. Don't worry, I'll walk you through an example in a minute. And then, on the far right here, we have the consequences of the model, or the state of risk. So for example, if you are a policymaker, you might want to have something tangible you want to measure, and so you can look at the hexagons here, and you will have economic, social, or environmental changes that you are able to measure out of this model. Here I have 3, for example. Okay, now stepping out of the modeling perspective here, I'm a field scientist, really, and I will just walk you briefly about a way that I could be using this model, or where my little bit of knowledge would fit into here to give you an idea. Those are pictures from my students this summer working in Cambridge Bay. They are collecting soils because we are interested in knowing how fast the carbon accumulates in the tundra, and also how fast the soil might be decomposing as the temperature is warming. They are also installing weather stations on these pictures. Now, where that kind of information fits in this model, well, we have the terrestrial carbon budget here that you can see. And if you think about big outcomes that a policymaker or another stakeholder might be interested in, that could be something like climate change abatement, right? So you have that connection there. But then you can work back way and think about what is influencing the terrestrial carbon budget. So things like CO2 emission, methane emission, DOC exports, those are all little bubbles on that diagram that point into the carbon budget. And then here you see what is influencing those fluxes. Well, we have respiration in the soil and plant production. And then you can go even backward more, and here you see the soil conditions themselves and their hydrology itself and how it's connected to the active layer depth and the change in permafrost. And then you can go even more back and go all the way down to the threats, which in this case, for example, and this is an incomplete picture, could be things like surface air temperature as well as snow depth. You can also think about humans that are changing the way that the soil is, and so that land cover plays a big role here. Now you can even step back further and connect it to what other people are interested in the room, such as, let's say, fire regime, which is a question that just came up a minute ago, or also how government, for example, could be interested in climate mitigation, and that could all be fed into this model. Now, a few short points here about this model here is that it reflects what we know of the system. Of course, we cannot move beyond that at this point. It also allows us to collectively contribute to this state of knowledge. Now I want to give the stage for a few minutes to Darcy so that she can give us an idea of a perspective from a local Arctic person.
Thank you. Thank you. Yeah, so I mostly, so I'm Darcy Peter. I'm Koyukon and Gwich'in Athabaskan from Beaver, Alaska. When I was asked if I wanted to help on this, I was like, oh yeah, that sounds cool, like a risk assessment, because there are a lot of those in the Arctic. And being born and raised out in Beaver on the land where we hunt, fish, and trap for our food and for our resources, I was like, yeah, there's a lot to say in a little amount of time. So basically, I'm a scientist also. I'm currently going to graduate school at the University of Alaska Fairbanks. So trying to find the balance between, Western education and a very traditional upbringing, was a little bit of a shock for me. But I think that this risk assessment model is really interesting for me because I see more of the modules that were on the right-hand side, the effects, just being out on the land. So just a few of the observations that people in my community in Beaver, and I think around most of Alaska have seen, are a later freeze-up in the fall time of the river, which obviously creates safety risks and a lot of hazardous conditions. But at the same time, we kind of need to hunt, and we need water, and we need fuel. So that's one of them, and to tie it back to all of the things that can cause that, there's a lot of snow depth, there's ambient air temperatures that are warming, there's water that's warming, and then going from that bubble down, you can also see a decrease in salmon populations in abundance, and everything is connected in this model. And so it was really, really interesting for me to look at all those tiny little bubbles. When she first sent it to me, I was like, oh my goodness, I don't know if I can read all that, but I think it's very applicable to life in rural Alaska. Everything impacts everything, as we all know by now, and it kind of just highlights everything that we're experiencing. And I think that it's important for policymakers because, you can read books and you can read papers and you can get a Western education, you can go through all the right steps, but until you get out on the land and see it and observe it and see how these impacts are directly changing the lives of these people who have had the least to do with climate change, it's really, it's a pretty powerful thing, and it kind of compels you to want to do more. So thank you for inviting me. Thanks for having me. I think that this model has a lot of potential, and I'm really glad to be here. So thank you.
Surprise for you. Click on the thing.
Sorry?
Click on the green arrow.
I did.
Yeah. Okay, click again. We started playing with the bubbles and thinking where your story would fit.
There we go.
So a lot of these purple nodes there where the human phenomenon are highlighted.
Oh, policies. Yikes. Wow. This is a surprise. Thank you.
It's incomplete, but.
Right. Thank you.
Now, a couple more things before I let Zenon explain to you what happens in the background of this model. This is not just a flow chart, okay, a flow chart. Each one of these nodes has real data attached to it. And in fact, he would not be happy that I said data, because I should use the word evidence, because it's data from observations and experiments. We can also feed to this model expert assessments and expert knowledge, and we can also feed model simulations. So those three types of evidence can be put behind each one of the nodes here. Okay, so you can think about the way the information would flow from left to right, such that every time the connection goes from one node to the next, you can look at the data and then the uncertainties that are going along with this data and how it kind of piles up together to lead you to the state of risk on the right-hand side. Okay, now what do we want to do and why we are here and why we need you? First of all, is that we want to find everything that's available into the Arctic community so that we can inform this model as good as we can. That includes, like I said, those physical observations, this knowledge, as well as model simulations. The other thing is we want to facilitate the use of resources that are also existing. And by resources, that can be human capital, it can be funding, it can be existing infrastructure as well. Now, by the same token, now that we, let's say, have identified everything that is available, that also allows us to identify what is not available and what we need, so the data and the knowledge gaps that are there. And those are the next steps we want to take. Now, after that, we also want to build that model that we saw, that we just showed you now. This is just our first iteration, and by any means do we think that this is our model. We think this is our community model. So we are looking not only for evidence, but we're looking for people who want to be part of the building of this model, and also people who might want to use it in the future. And that takes me to the most important point, that is to foster a community of Arctic stakeholders. And finally, guide the policymaking that, of course, would come after this model is working. wrapping up. It's just such a nice slide. I need to show it to you again and again. Now, one last example of how someone from the decision-making perspective could be utilizing this model, it's to go from the right side and work our way towards the left side. So here I said that you can run the model in a diagnosis, which means just reverse modeling. So let's say you are interested in sustainability of a shipping and a cruise ship road in the Arctic, but you really want to know more about the infrastructure and the biodiversity in this adventure. Then you can backtrack what would be influencing the state of risk of these two hexagons here. And I'm trying to show you this, okay? So then you could look back, for example, at where the existing transport infrastructure exists, what kind of Coast Guard you already have in place for safety and operation. You can look back and think about what exists in terms of tourism already and public infrastructure, and you can go on and think about coastal flooding or coastal erosion, all the way back to fog. That would be pretty important. And finally, what kind of global economic structure exists. So now we are welcoming your thoughts and your questions already, although we're just halfway through this talk, so that, for example, are there threats that, as I've been speaking and as you've been seeing this model, are there threats that you are facing? And if so, what are they what are they affecting? Or are there specific environmental, social, or economic consequences that come up to your mind? And maybe we are already portraying those in the model, but perhaps we are not. So we need to know about this. Also, is this reflecting your vision of the Arctic? And are these nodes and connections capturing your perspective? So I will leave you to this, and you can start answering to these questions and send them to us, but I will not take them right away. So you can think about it, and I will give you the microphone.
Okay, thank you, Julie. So I guess, which one is forward? Should I be closer to the computer, maybe?
The other one. This one.
Oh. Okay, very good. Okay, so what I'm going to do is going to go through now the simplest way in which we can explain how this model works. And we're going to aim at proving to you that it works. And actually, we're going to show you several examples where it has actually worked. So let's go to the basics. Decision-making is the ultimate goal of what we would like to achieve by introducing this model. We want to improve decision-making for decisions that could lead to a sustainable Arctic ecosystem. So this is an exercise that was run last year, but it is actually run every year at the World Economic Forum. And in this case, we have close to 900 respondents from different countries all over the world. And people are asked, so what are the events that they see as more significant, having a potential impact at a global scale? But they also are asked what are the events that they think are the most likely to happen. And here we basically have these two components. Which one is the pointer?
Yeah.
This one, okay. So on the x-axis, we have the hazard. So this is the likelihood of these events happening. And then here we have the impact of the consequence, and what we have on the y-axis. You see some color codes, and you don't need to have great vision to get to read the details here. I'm going to make the effort to read this for you as well. But what we see is that what we find in this study is that the most likely events to happen with the highest impact are those that are located in this corner. And you see that you have three green dots. One, the most impactful and the most likely to happen is extreme weather events, followed by natural disasters, followed by failure of climate change mitigation and adaptation. Now, if we look at the most impactful, is this one. This one is slightly higher than this one, and this is weapons of mass destruction. So this is according to this questionnaire, this is not the most likely to happen. The most likely to happen is this one. But in terms of impact or consequence, this is very close, or these are the most, relatively speaking, most relevant for global stakeholders. Now, you see that there are all the colors. So blue are economic events, green environmental, orange geopolitical, red social, and purple technological. So we have cyber attacks here, right? So, and believe it or not, this is unmanageable inflation, economic inflation. But this is not a stationary assessment. So what I want to show is that if we look at what has happened in the past 10 years, this is 2008, this is 2018, and this is a ranking of the top 5 most likely events to happen globally. And as you can see, 10 years ago, we have a lot of blue. So we have asset price collapse, we have slowing Chinese economy 10 years ago, right? But when we look at 2018, in terms of most likely events to happen, we have extreme weather, natural disasters, cyber attacks, data fraud, failure of climate change mitigation and adaptation. So these are what global stakeholders are perceiving as the most likely events to happen nowadays. Now, in terms of impact, so I have mentioned, number 1 is weapons of mass destruction. And still we have this green coming up again. But look how much blue we had in terms of impact perception in 10 years ago. So what I want to say is that our perception of the state of risk, which is given by these very simple 2 components. So what is it that is most likely to happen, which we call the hazard, versus the most impact or consequence that these events can cause, then it gives us this sense of the state of risk. And we actually define it formally here. So again, if we multiply hazard times consequences, then we get a value of risk. Now, Julie mentioned that I'm an engineer. And my expertise is looking at risk assessment of processes that are changing in space and time. And I love processes that are sharing the same domain, multiple processes at the same time that are moving in time. So that's the expertise of my research group at CNN. So in engineering, the risk theory emerged after some nuclear failures. And at that time, we realized that we needed to add this additional component that is called vulnerability. And many of you already have used this word today. And Julie already mentioned it in this big model, and we're going to go back to that in a second. So let's define this according to the engineers that came up with this specific definition of what hazard is. So in the previous example, stakeholders were asked to rank from 1 to 5 the intensity of this likelihood and intensity of the impact. For engineers, when we're looking at infrastructure and natural phenomena threatening the infrastructure and the potential consequences impacting of these threats and these vulnerability systems, then we're talking about probabilities. So the hazard for us is a probability, is the probability of the intensity of the threat. And then we have vulnerability. And this is also probability. And this probability is actually a very special probability that is called a conditional probability. This is a probability of reaching a certain damage level to the system conditioned on that threat intensity. And then, so we have a probability. So what is the range of variation for a probability value? Between 0 to 1, right? So that means that the first factor here is going to range between 0 and 1. The second factor here is going to range between 0 and 1. And this is actually the value of the element at risk. So if we have people that are exposed to a particular threat that is sustained by a particular system, so this is going to be a potential life loss of people getting sick. If we're talking about infrastructure, the value of this consequence is going to be monetary, so it can be economic loss. Or if we have an environmental loss, so we can talk about hectares that have been lost, or biodiversity that has been lost if we're talking an environmental consequence. So it was 2006. I was working for the International Center for Geohazards at the Norwegian Geotechnical Institute in Oslo when I came up with this idea. So this risk framework has been used in engineering for decades. And then I was coming across an easy way to represent complex interactions between multiple threats, multiple vulnerabilities, and multiple consequences. In engineering, we do decision trees or event trees to represent that, but they are not easy to work with other experts, and especially with people that are exposed at risk that know nothing about probability. So this is a very simple way to represent this very same equation. So this was an eureka moment for me, because I realized that this is a mathematical model that is called a Bayesian network. And this Bayesian network represents this very same equation that you see here. So you see the probability of the threat. So then that means that this node is containing a state of probabilities. And then the probability of the consequence that is conditioned on the threat. So I cannot have a consequence if I don't have a threat. And that's basically what this probability is saying. And finally, when I multiply these three factors, what I get is a convolution that is going to give me an estimate value of the state of risk. So basically, this very same equation that we've been using for decades to estimate risk assessment, we could represent it using a Bayesian network. And when I realized this, I was like, wow. That means that we can represent now multiple threats, multiple vulnerabilities, and multiple consequences of highly complex systems. And we can share this with anyone because it's as simple as representing the identification of the threats, the consequences, and what we want to assess in terms of risk. So, but as I mentioned, that equation is again right here, and that equation only represents risk assessment. Once that we set the basis of what is the state of current risk, if we don't like it, if we think that we're above what we can sustain in terms of life losses, economic losses, people getting sick, or environmental losses, or social losses, other types of social losses, then we start thinking, wait a second, we need to do something about this. So what about improving monitoring systems? Or what about changing policy? Or what about creating these new government programs? Because there are ways in which we can aim at reducing the threats. So if we reduce carbon emissions, we might be reducing the climate threats. Or we can move people, right, to higher ground. So that means that they are not going to be exposed to a potential flooding consequence, right? So we can start thinking on policies that we can implement so that we can reduce the state of risk. So that means that these active countermeasures and these passive countermeasures are going to help us reduce the state of risk. But that's going to cost us. And that's our last term here. So whatever policy we implement, whatever monitoring system we implement, whatever research we add to the equation to reduce the state of risk is going to cost us. And then we have a trade-off, right? But at least now we have a very simple, extended way. So now this model is representing risk management and risk assessment at the same time. So how is this going to work in simple terms? So I'm going to walk you through these very simple examples. So let's say that we have snow precipitation, and we're going to use these very simple descriptors that are low, medium, or moderate or high. Actually, what I have found in my experience working with multiple disciplines and with communities is that they don't care about the temperature value or the pressure or the rain precipitation. They just want to know if it is going to be high or if it's going to be low. So we can translate, and that's why I'm going to use these very simple terms here. So we have a description of the snow precipitation, and then we have this particular potential damage to a house in the roof system of the house, right? So that's going to be my consequence. And then I have the corresponding cost that, again, is low, moderate, of high. So if I have low damage, or if I have moderate damage, or if I have high damage, so what would be the corresponding monetary cost? So this is the same equation that we introduced before, risk assessment. But now I have a probabilistic description. So this is a probability density function of what low snow precipitation, moderate snow precipitation, or high snow precipitation. And then here we have also probability distributions that are representing, if I have low snow precipitation, what is the potential for damage? If I have low snow precipitation, what is the potential for having a moderate damage? If I have low snow precipitation, what is the potential for having high damage? Now, if I have high precipitation, so this distribution that I have for low precipitation basically reverts, right? Now, but for me to come up with these values, which are probability values, and to come up with these values, I need to investigate the threat. I need to document roof damage for a specific threat intensities, and I need to know what is the cost of having low roof damage, moderate damage, or high roof damage. Now, when I run this model, so I'm going to show you very quickly. So I'm not going to go through the mathematics of this, but there is mathematics involved. So yeah, engineers, we also do mathematics, by the way. So we run the model, and we come up with what is the expected value of risk, right? So again, this is the probability density representing the state of snow precipitation, roof damage, and the corresponding value of economic risk. Now, I want you to pay attention to this value. So this was roof damage due to snow precipitation. Now, let's present a second case. Now let's do not talk about snow precipitation. Now let's talk about wind. So wind is going to have its own probability density function, which is based on either historic data, model predictions, or if we don't have data, and we don't have model predictions, who do you think we should ask? People. So you've been saying, we want to have this compound or integrate right there. That's the beautiful thing about probability theory, that can encapsulate these three distinct components of what in Bayesian inference we call evidence. Physical observations, historic data, model predictions, or people knowledge. So same for the vulnerability, but now we know that this wind threat can actually generate more damaging effects to my house. So now we're talking about not roof damage, but now we're talking about structural damage. So it's not the same if you have roof damage at home, so your house can keep being operational. But if you have structural damage, you might need to evacuate your house, right? Because it might be at risk of collapse if it is severely damaged. So we follow the same approach, and now look at the values of this low, moderate, or high structural damage. So the order of magnitude is higher than the case of just the roof damage. Now we're talking about the full structural damage. So we run this model again, and now we have this expected value of risk. Now, as I said, when I realized that we could simulate this very simple equation of risk, it was because now we can have multiple threats, we can have multiple vulnerabilities, and we can have multiple consequences. So now I'm creating a new model where I see that there is the possibility that if I have structural damage, roof damage, that it can create structural damage. Sometimes, if we do not fix the roof, it can create structural damage. And that's basically what we are reflecting here. But now we're not looking at this independent model or this independent model. Now we're coupling these two because we realize that they are connected. And in addition to that, now we're introducing a social potential consequence to the household. And that is associated to having 0 people being injured, 2 people being injured, 4 people being injured in a household of 4 people. So now I can run this model, right? And what I can generate is simultaneously, for multiple threats, multiple vulnerabilities, and multiple consequences, the corresponding economic risk and the corresponding people getting sick. Now, when you go and talk about this to a stakeholder in a community, when you talk to the tribe leader, when you talk to the mayor, when you talk to the governor, they don't care that much about this. They care about this. They need to know how much money we're going to lose. Are we going to be able to recover after this snowstorm? How many people is going to be injured? So what we wanted to say is that independent risk assessment is not the same as compound risk assessment. And we have the ability to do that. Now, next is, I mentioned that I have this breakthrough when I work in Norway. This is an early warning system for Norway's #1 natural hazard threat, which is this massive rock slide in Agnes. And if it falls, it might wipe out the surrounding communities and also probably kill all the visitors on these cruise ships that visit every summer. So we needed to put together all the scientists and all the community leaders so that together we can come up with a model that could reflect when to issue a warning system to go from green to yellow, yellow to orange, orange to red. Another application is on water quality and natural resources. Another application is on dengue epidemics. Another application is on restoration activities in the Gulf of Mexico. Another application is in the selection of shale gas drilling systems for environmentally drilling practices. Another application, and this is my favorite. So far we have presented a model that we assume is going to be applied to a special domain. But now we can show that we can run that model if we do a segmentation of the spatial domain. So if you have remote sensing data, satellite data, if you have ground truth data, if you have model predictions, we can put them together as long as they are associated to a specific spatial domain, and that can lead us to a risk map. So the model that Julie presented before, and that I'm going to present again here, right, was produced by consulting with more than a couple of dozen experts. And these experts, the first question that they asked were, can we map this? And the answer is yes. All what we need to do is to run the model. Now, somebody will ask, do you actually have experts for each node? The answer is no. But this model is letting us see where is it that we need to develop human expertise. The next question was, do we have databases for each one of these nodes? And the answer was no. We actually don't know. That's what Julie asked you at the opening of our presentation. We need your help to run the model. We need to know who has the data. We need to know who has the knowledge. We need to know who has the models. Well, we already met one that is extraordinary, modeling Earth systems. But we need to know what is it that you can contribute to our model. And as Julie represented before, so this big model is nothing else than this very simple model. The complexity is much higher, but I just proved to you that it works. Okay, now where are we going to start? So now I'm going to wear my hat of engineer. We need to start with the simplest model representation. And this is what we call the minimum conceptual model. So that big model now is being reduced. And we would like to run this model where we know that we can already have some support from experts, some support from data, and some support from models. And for that minimum conceptual model that we're ready to run, we need a leader. And that's Julie.
Oh boy, thank you. Like Zenon was just saying, we ask you, what type of evidence do you have to contribute to this model? Remembering that evidence includes data, model simulations, and expertise. Are we missing anything in this model? And I hope the answer is yes, because definitely we're missing a lot of it, and we need you to point those out to us. And here I will reiterate the first questions that we posted 20 minutes ago, in case you were still pondering about those. And one last thing that we have not mentioned in this talk yet is, why do we need this, and why do decision makers need a model like this? Besides assessing the state of risk of indices that they might be interested in, the reason why Zenon and I started this is because we really want the scientists to be at the table. The Arctic is a place that is, we heard today, a lot of people see as a land of opportunity, for better or for worse, or it depends who the opportunity is for. But what matters, at least from our perspective, is that the science is at the core of the way that the decisions are being made. Because decisions will be made regardless. But we think that we as a community should have a word to say, and we think that a model like this really brings up what we know and what we can offer. So I will leave this up for you, but before, actually, I just want to say that thank you to our team at Texas A&M. So I put their names here. Our poster looks like this, so if you see it, if you want to look at all the notes, you actually can read on the poster what it says. So please stop by on Thursday. And on this, yes, please send away the questions.
Yeah, here, I'll move up here. So I think this is really important because it's quite clear that you're interested in engagement and contribution. And I'm wondering what opportunities or challenges there are for having a funding model that supports Indigenous knowledge integration and the observation, sharing, and engagement that's required so that those people can be, appropriately and equally paid. So often this is a challenge that the Western scientists have funding, and what does that look like for people contributing on the other side?
I envision that, the deliverable of this effort, this is just 1 year effort where we spent a lot of time talking to experts and reading about the local communities and interacting with local communities. But we won't produce anything that is not useful for the local communities and to the public in general, right? So we thought that mapping is something that is very versatile and that could give us a tool that could change the probabilities on the threats, the vulnerabilities, and the consequences to play with different scenarios. So what happens if we move now this community here, or what happens if we have flooding in this area, or what happens if suddenly this year the temperature is going to increase. But we can also go, as Julie mentioned, on the other side. So if we want to preserve the communities, if we want to preserve the environment, what is it that we need to control to keep it as we want it? That the model can also tell us. So, but this has to be communicated to the community and to the scientists in plain language. So that anybody could go in maybe a virtual environment, maybe online, so that we can play with these different scenarios. We envision also an outreach effort. So from the first group of experts that we started working with, we heard the education is both ways. So, and I think this is a fantastic platform to interact with all the stakeholders so that we can learn about what are these parameters that you're willing to preserve where they are, so that we can mobilize whatever we need to mobilize to keep it as you want it to be. So 2 answers to the question. One, physically, we're thinking that maps could be a very nice way to interact and also to introduce technology and to see real-time monitoring. So there's so much technology development, expertise, model predictions that we can in a simple manner interact with. But it's a learning process. And I love, somebody mentioned that this morning. I mean, just the exercise for us to build a model has been a wonderful experience. I mean, we cannot imagine when we extend it to the communities that are going to basically be the users of the model that we're proposing. I don't know. Okay.
As you think about using this model, do you think it can be used too for determining kind of important data or indigenous knowledge gaps, so that we can identify those and think about identifying the gaps, especially if we're interested in particular consequences?
Absolutely. Yes, we think that in addition to bringing everybody together, it will not only highlight what we don't know, it will also highlight what we should really put a lot of emphasis on. And we're hoping that, let's say we have a complete model version 2 to work with. People can go to an agency, a funding agency, and see, this is the Arctic, this is what I study, and this is what it matters because it's connected to these 18 other things. Something that is not that easy to otherwise transcend in a regular proposal. So, yes.
And then I think for our last question, can you talk about, you use the language of threats, risk, and can you talk about how you can use the model to identify opportunities and kind of in a more
Thank you for asking that question. I mean, like in many of our disciplines, sometimes we inherit terminology that came from an era where we have a nuclear threat. We needed to look at vulnerabilities and consequences. So this is the vocabulary that we still use in risk theory. But absolutely, and we're actually exploring ways to rephrase and redefine these terms in a more constructive manner. Yes, risk is something that everybody reacts not positively, but as Julie mentioned, I mean, to know that you're on a very low state of risk is something very good. Maybe we can reformulate, we define these terms, so that we can convey the same message, but maybe in a more constructive manner. Absolutely.
Excellent. Well, thank you all so much. Let's thank them for showing this beautiful model and hopefully giving us all some inspiration to interact with it too.